In this lesson, we're going to see an application of derivatives that can help us to figure out complicated limits. This is something called L'Hopital's rule. L'Hopital was a French mathematician, or actually a rich French guy who paid some tutors a lot of money and communicated with some really smart people like the Bernoullis, and eventually printed one of their theorems because he had lots of money. He could do that, and so he claimed the theorem for himself. So there's a little bit of scandal going on there, but this guy L'Hopital here gets the credit for this rule. At least he gets the name for it. So here's the situation. We have some functions that are rational functions here, and we have some situations where we've got limits, and we have some ways to figure them out that we've developed, like this limit here. When x goes to 3, it's going to 0 over 0. Well, we can factor these if we figure that out, and we can clean that up so that we can actually figure out what the limit is there with that one. Then we've seen limits like this one, where x is going to 2. We get 0 down here and 0 on top. Well, we have another way of dealing with that. We multiply by the conjugate of the top. Remember doing that? And then we rationalize the numerator. Then we had this situation where this limit going to 2 gives us 0 on the bottom. When you plug, as x goes to 2, this goes to infinity. So it gets gigantic. So we got infinity over 0. Well, that's something we can't really figure out. So if we multiply and clean this up, get rid of that compound fraction, we can figure out what the limit actually is. That's how we deal with those. And then we had limits like this, where we're going to infinity, and we had some ways of dealing with this. This is going to infinity over infinity, and we kind of just said, well, when x is gigantic, like a billion or a trillion, the 4 doesn't matter, so this just becomes 3x squared over 2x squared, which is really 3 over 2. So that's how we dealt with that. Well, we had some strategies that worked with those kind of expressions. However, those will not work with expressions like this. Here, the limit is going to, as x goes to 0, x is going to 0, and 2x is going to 0. So, we can't use any of those strategies we just had there, okay, because you can't factor e to 2x and such. How about if we have like natural log of x over x? Well, this is going to infinity. X is going to infinity, so this is going to infinity on the bottom, and the natural log goes to infinity also. So we can't evaluate this. This is not 1 because infinity is not a number. Okay? Or x squared over e to the negative x. Doesn't fit any of those models. Or as x goes to infinity, this thing is going to 0 times infinity. So all of these are cases that we can't really deal with. Same thing for sine of x times x here. We end up with, as x goes to 0, this is 0 and this is 0. Well, does that mean 0 times 0 is 0? Not really. We can't just say the limit is 0 there. Okay? So these are what we call indeterminate forms. So first important thing when working with L'Hopital's rule is we need to understand what it means to have an indeterminate form. And specifically, all these indeterminate forms involve 0 and or positive or negative infinity. All right? So notice that, okay? They're all going to, either the top and the bottom or the first and the last are going to 0 or infinity. So notice that, okay? Now, if you think about a function like this, 2x over x, well, that's going to infinity or infinity as x goes to infinity. But we can see that no matter what the number is, the top is always going to be twice as big as the bottom. So that's enough just to say, well, that this limit, this infinity is twice as big as this. This number on top is always twice as big. So infinity over infinity doesn't mean 1. In this case, this is going twice as fast. So the limit as x goes to infinity of 2x over x is just the limit of 2, which is 2. All right, so these were problems that this guy L'Hopital was investigating in the 1600s. All right. And as I mentioned there earlier, he really got lots of this information from a guy named Joseph Bernoulli, who made lots of scientific discoveries as well. And they were working with limits that ended up with these forms. These are our indeterminate forms, right? And we want to kind of remember these. The key ones are 0 over 0, and then plus or minus infinity over plus or minus infinity. Those are the main ones. Now, these limits can be expressed in these fractions, but that's the key there, 0 over 0, which is really what L'Hopital's rule originally states. But the rest of these, we have some kind of techniques to change them into 0 over 0. All right, well, let's investigate some here and see what the rule says. So that was a lot of setup to say what the L'Hopital's rule is, all right? But that's important setup, because if we don't have one of those indeterminate forms, you can't use this. So here's the deal. If we got two functions, f and g, that are differentiable on the interval ab, and they contain c, which is the point that we're going to here, and we'll assume that the derivative of g is not 0. Okay, so the derivative of g, notice we're going to have a fraction here, f of x over g of x, that we're trying to find the limit of, all right? So we can't have 0 on the bottom, all right? So here's the deal. What the L'Hopital's rule says is if the limit of f of x over g of x, as x approaches c, produces the indeterminate form 0 over 0, then we can find this limit of f of x over g of x by finding the limit of the derivative. Or, another way of saying that, the limit of the ratio of the functions is equal to the limit of the derivative of the functions. Notice we're taking the derivative of the top and the derivative of the bottom. We're not taking the derivative of this whole fraction. Very important note we got over here. Okay, don't confuse this here. We're not saying that the derivative of f of x over g of x is f prime over g prime. That is not true. You know the quotient rule. We've talked about the quotient rule. It takes a little bit more work than that. Okay, this is only for limits. The limits are equivalent. That's why we're going to write limits, and keep writing limits. Okay? Now, this also applies to some other forms, infinity over infinity or negative infinity over infinity, okay, as well. And then some other ones, special ones. So, all right, but the original theorem was for 0 over 0. So first thing we've got to do is we have to test this out. So we've got to do some direct substitution. And we've got to say, all right, this is e to the 2 times 0 minus 1 all over 0. We're substituting for 0. And that is on top, 2 times 0 is 0. So that's 1 minus 1 over 0, which is 0 over 0. All right, so it checks out. This is an indeterminate form of 0 over 0. That means L'Hopital's rule applies. All right, L'Hopital. All right, which in French, I believe, means the hospital. All right, so let's see. Let's go to the hospital. L'Hopital's rule. Let's fix this up. So this limit is equal to the limit as x goes to 0 of the derivative. Well, what's the derivative of x? 1. The derivative of the top? Well, we're going to need that. That 1 goes away. Chain rule here. Derivative of the inside is 2 times e to the 2x. Remember, when we find limits, our ultimate goal is to do direct substitution. Just plug the number in. Up here, 0, when we plug it in, is a problem. Down here, 0 is not a problem. So we plug it in, we get 2 times e to the 2 times 0, and that's all over 1, which is going to be 2 times 1, which is 2, over 1, which is 2. There we have it. So the limit is 2. All right. So if we take a quick look at this here, we can see there's the function that we just found the limit of. And if we trace this here, we can see as x is coming close to 0, watch that y coordinate. That y coordinate is getting close to, we better zoom in here, that might help. There we go. As x is getting close to 0, y is getting close to 2, and then it's undefined there. Okay, so the function itself is undefined. However, we see it's getting close to 0. All right. So the ratio of the derivatives, the limit of the ratio of the derivatives gives us the limit we're looking for. All right. Well, what if we have an indeterminate form of infinity over infinity? Well, here, if we're going to infinity and we plug in infinity, which you can't, okay? You can't, infinity is not a number, you can't really plug it in. But think of as x is a billion. We have the log of a billion, which is still a pretty big number, over a billion, okay? Think of the graph of log. The graph of the natural log of x goes like this, and it keeps climbing. Even though it climbs slow, it keeps climbing, so the y value gets bigger and bigger. So this is going to infinity over infinity, so check. We've got to check it first. We've got to show that. So we need L'Hopital's rule. All right, we've got to use L'Hopital's here. So the limit as x goes to infinity of the natural log of x all over x is equal to the limit of its derivatives. So the limit, we haven't found the limit yet, so we're just taking the derivatives. Derivative of natural log of x is 1 over x. Remember that? Derivative of x is 1. All right, so we can clean that up. We don't need the 1 on the bottom, so this is just the limit as x goes to infinity of 1 over x. Okay, and as x goes to infinity, we have 1 over a million, 1 over a billion, 1 over a trillion, and that's just going to be going to 0. So that's a limit we need to be familiar with. That's 0. Okay. Again, we've got to check out to see that we have one of these indeterminate forms. Okay. Well, sometimes we've got to use L'Hopital's rule more than once. In other words, we've got to use a derivative more than once. So let's see what happens here. So first, let's check it out. As we go to negative infinity, negative a million squared, negative a billion squared, so on and so forth, that's going to infinity. Okay, negative a million squared is a big number, a big positive number. What happens when we plug in negative a million into here? We have e to the negative a million. Well, that's a power of a million, positive a million. That's going to another huge number. All right, so we need L'Hopital's rule. All right, L'Hopital's rule is going to be applied here. So we're going to say the limit as x goes to negative infinity of x squared over e to the negative x is equal to the limit of the derivative. So we're going to take the derivative of the top and the derivative of the bottom, not the derivative of the whole fraction, just the derivative of the top and the bottom. So x squared is going to go to 2x. And e to the negative x, well, let's use some chain rule here. Derivative of the inside, which is negative x, is negative 1 times derivative of e to the negative x, well, the e to the u, that just is a copy. Well, as x goes to negative infinity, this is going to 2 times negative infinity, which is going to negative infinity. On the bottom, this is e to the positive infinity, so negative negative. That's gigantic times negative 1. So this is now going to negative infinity over negative infinity. Okay, well, we need L'Hopital again. All right, so we're going to do another derivative again. So, because we're not at a point where we can just evaluate it yet. We can't use direct substitution yet. So we take the derivative of the top, derivative of the 2x, and that's going to be 2. Derivative of the bottom, and little chain rule again. Derivative of the inside is negative 1 times the negative 1 we already had there was 1 times e to the negative x. We obviously don't need the 1 there, but okay. So we have 2 over e to the negative x. All right, and now as x goes to a million or billion and negative, so e to the negative million, that's e to the million, or e to the billion, that's a gigantic number. We have 2 over a gigantic number. 2 over a gigantic number is 0. There it is. Okay, so if L'Hopital's rule doesn't give you what you need for direct substitution once, then use it again. All right, so that's how L'Hopital's rule works. So we'll leave it at that, and hopefully that helps give you some framework. Remember, we always need to check to make sure that we meet one of the requirements, which is the standard ones are 0 over 0 or some fraction involving infinity. All right, we'll see some non-standard ones when we look at some more examples.